Before we move to the technical details, I would like to review the agenda of this webinar. So in the first time, we'll review the background of the electrical vehicles market and understand together why we observe a growth of it. Then we will understand what are the related industry challenges and see how and why MSC Solutions can help you to solve your engineering problems. And finally, as Ijun said, we'll review the different workflows that exist, some case studies, and conclude by a live demo. So, since 2010, the electrical vehicle market is a growing one. Different electrical vehicle technologies are present, from the hybrid electric vehicles, or HEV, to the fuel cell vehicle, or FCV. But according to projections, the BEV and PHEV will be the dominant technologies in the coming years. This growth is actually driven by regulations. All major automotive markets in the world do have emissions regulation in place. These regulations are diverse depending on the countries, but all aim at reducing the emissions of CO2 and improve fuel economy. For instance, if we look at the European CO2 Regulation, 2020 will mark the entrance of a new CO2 regulation, and the target will be joined by an excess emission premium for manufacturers failing to meet the target. Looking at the different emissions performances, the 2020 regulation is actually asking a 27% emissions reduction to all OEMs. This will lead to more or less important efforts for each of them. In order to achieve this reduction, electrification is needed, explaining the electrical vehicle growth that we previously seen. But the question now is, what are the NVH challenges related to this growth? To understand that, let's have a look at the total interior noise of an internal combustion engine. We actually know it's the sum of powertrain noise, tire and road noise, wind noise, and auxiliary devices noise. Now, if we look at electrical vehicle noise sources, the removal of the powertrain noise will, by definition, reduce the amount of noise sources, and as a consequence, make electrical vehicles quieter. But is it that simple? Do we, as NVH engineers, can rely on this simple statement? The answer is no. Despite the removal of one of the main noise sources in cars, there are numerous remaining NVH challenges to tackle with. The very first one concerns the remaining noise sources that are now not anymore hidden and dominant, and that will potentially annoy the driver experience. We will add now the electric powertrain noise that need to be considered. Usually, EV vehicles are perceived as high-tech vehicles, increasing passengers' sound quality expectation. And finally, if we look on the exterior noise, having a total noise level that is decreased can impact the pedestrian security, making electrical cars a potential threat. This creates a various and complex landscape that NVH engineers have to tackle with. Generally speaking, we can consider two ways of dealing with NVH issues. When customers complain about noise, the engineers have to work as surgeons and quickly fix the problem on an existing product. Of course, avoiding the acoustic issue before would be better, and this is of course an advantage to integrate NVH analysis during the development process. In this way, simulation can offer solutions with obvious advantages. We can know the noise level before prototyping. We can easily integrate results from other calculations in our simulation. And at the end, we better understand the physical phenomena. Actually, MSC Software provides a complete end-to-end solution to address these problematics. Multi-body simulation with ADAMS can provide you with the structural loads when the powertrain is operating. MSC Nastran is the industry-leading tool for vibration analysis. And Nastran can accurately and efficiently compute the noise radiation. Finally, electromagnetic simulation results from various softwares can be easily integrated with MSC tools for electric motor noise prediction. Now let's better understand how the MSC software solutions can be used for electric powertrain noise simulation. Actually, there are different technologies for electrical powertrain. But whatever the architecture, any electrical vehicle powertrain does include an electric motor and a reducer. The gear reducer and transmission noise can be efficiently studied using MSC Nastran, ADAMS, and Actron. While on the other hand, electric motor noise can be studied using MSC Nastran and Actron. I will now give the floor to my colleague Ijun, who will present you the MSC solutions for gear and transmission noise. Ijun, I give you the control.
Thank you, Romain. Okay. Let's take a look at the gear reducer and transmission noise first. So in order to predict the noise coming from this moving mechanism, we need to be able to capture the three phases of the physics. First, you need to have some kind of tool to calculate the system loads that's generated by this mechanism. And secondly, you have to capture the surface vibration of the gearbox casing. And after that, you will be able to perform an acoustic radiation and produce the noise results, or get the noise, actually come up with the sound of the actual mechanism when you have all those three steps produced. So the essence of the gearbox noise can come from either gear rattle or gear whine. But both of them are starting from a gear mesh force, and we need to be able to capture how that force can be transmitted through, for example, the bearing force all the way through the body vibration in order to generate the acoustic radiation. And for capturing both the gear rattle and gear whine, we have different applications for that. For the gear rattle noise, it's more of an impact-induced noise. So you need to be able to accurately incorporate the 3D geometry and how the different gear pairs are contacting each other. So with the traditional Adams machinery 3D contact gear, you will be able to definitely incorporate the gear rattle into your system level analysis, and later analyze how that gear rattle vibration can be transmitted all the way through the gearbox and then into the acoustic domain. For the gear whine, we're also coming up with a gear tooth deformation prediction tool, which will allow you to consider or account for the flexibility of the gear tooth. And when you can capture the realistic gear tooth flexibility, you will then be able to capture some of the deformation and also the vibration that's caused by the gear tooth deformation. So that's very important when you're predicting the gear whine noise. In this technology, an FEM model is actually created and solved in the background to help you define the tooth compliance. So Nastran is embedded into this technology when you are analyzing the gear tooth deformation. So as we talked about before, you need to be able to capture three steps of the physics: the loads, the surface vibration, and also the acoustics. The traditional way is for you to do those separately. So when you generate the loads from, for example, a multi-body system like atoms, you will import import loads into an FEA software like Nastran. Then you can calculate what is the surface vibration. After that, you will provide the surface vibration results into an acoustic tool like Actran to do the acoustic radiation analysis. That's the traditional process. And recently, we've invented a more integrated workflow, which is more user-friendly for MBD engineers, which means the acoustics, both the surface vibration and acoustic analysis can be performed inside the Atoms environment, which means you don't need to get out of your familiar MBD environment to perform those analysis. So that's very convenient and applicable to anyone who is a system engineer or multi-body dynamics engineer, who wants to understand the preliminary results or some of the early results for the acoustics without leaving your familiar kind of MBD environment. And if you want to do some advanced post-processing, you can always use the results you are generating with this simulation and post-process that in your in a more sophisticated acoustic environment like Actran VI. So next, we're going to show a brief demo about, it's a recorded demo to show you how the process looks like. The model we're using, it's a very fairly simple, like cooler system. So it's a very traditional Atoms model. You have the surface cooler as the flexible body, and also you have some gear system, the planetary gear and also gear pairs. So now let's perform a simulation with only the multi-body dynamics simulation. So we have one flexible body and some gear pairs. And later we want to analyze what is the acoustic radiation coming from this motor casing here. Okay, after we're done, let's do some simple analysis with what's the bearing force, and also let's perform a FFT transformation and study the frequency domain results. So all these are performed using pure Atoms and MBD results. Acoustics are not involved at this point. And now let's actually loading the actual toolkit that we're developing. It's called the Atoms to Actran toolkit. So go to the plugin manager and loading that new plugin toolkit. And when you have that, go to the Actran analysis submission. Then you can choose the flexible body that you want, which is the housing of that motor. Then you can define during that 1 second of MBD simulation, what is the time period for you to perform the acoustic analysis. Then you can define the mesh along with some of the other properties. And you can also create acoustic mesh within within this Atoms environment, because we are in the background, we are using the Actran technology to help you do those pre-processing. And also later, when we start running the simulation, there's a Actran running in the background to help you calculate those results. So when you click OK, we're done with the setup, just click OK. Then the acoustic simulation will be started in the background. Again, you're not leaving your familiar MBD environment. Everything is performed within this Actran Atoms interface. It takes, for this simulation, it took about 5 to 10 minutes to finish. And when you're done with the simulation, you can actually go to the post-processor and loading the acoustic results. So you will be able to import the acoustic file directly into your Atoms post-processor. And for that, you will get some of the acoustic analysis parameters. For example, what is the overall acoustic pressure at all microphones? The sound pressure level at certain microphone. You can also get some of the other preliminary acoustic results. In the latest toolkit, we're actually enabling you to not only get the time domain results, but also the frequency domain results, like the waterfall charts and things like that. So at this stage, if you're not happy or if you want to do some comparison, you can always go back to your mechanism. For example, you can change your gear configuration. You can change the gear tooth number or tip relief, some of those parameters that you want to modify. And then you can understand, you can perform another acoustic analysis in the Adams environment and compare the acoustic results and see whether or not those changes are good or bad for your final design. So this is a very simple explanation of the toolkit we have that enables you to perform the acoustic analysis, for example, for mechanisms like gear reducer or gearbox, all inside the multi-body dynamics interface. Okay, at this point, I'm going to pass the presenter. So this is to show you how you can change some of the gear parameters within the Adams environment. Okay, so at this point, I'm going to pass the presenter back to Romain, and he's going to take you through the rest of the presentation.
Yeah, thanks a lot, Idjon. That's a very nice tool that we have now. And as you said, what is important is that in the next release of this toolkit, we enable you to perform acoustic radiation analysis not only in time domain but directly in frequency domain, so that you leverage on really better performances and you can handle very large domain now. A nice illustration of this Adams to Actron interface is one case study and one application made at Ford, where they were interested in studying some gear and teeth design and assess if the geometry design will lead to rattle or whine noise. So in this slide you can see one of the geometrical parameter they played with, which was the pressure angle of the gear teeth, and they compared two angles in this case, assessing what would be the impact on the contact forces at the different orders, so showing that reducing the angle was improving the first order while reducing the performances of the third one. But this is the first analysis that you can already have within Adams. But what is interesting is to add on top of this force and contact force analysis, the acoustic analysis. And this is what they've done. So they use the Adams results, the vibration of the engine computed directly within Adams to perform an acoustic radiation. And thanks to this easy interface in between Adams and Actron, they could easily generate acoustic radiation results, but not only charts, but also listen to what will be the impact and the changes on the gear level, on the noise recorded at several microphones, so that they could listen to the impact of those changes and easily assess if whine or rattle noise was present. That was a very nice study made by Ford. Having reviewed the gear reducer noise and the MSC solutions we have for that, I suggest that we move to the electric motor noise prediction and understand how you could leverage on MSC solutions to handle these problematics. Actually, when we look at electric motor noise, the primary noise radiator is actually the stator frame. So when we do have electromagnetic forces that are applied on the stator frame, when the engine is operating, and if the frequency of these radial forces on the stator teeth are close or equal to any of the natural frequencies of the stator frame, we might have a resonance that will occur. This resonance can lead to deformation of the stator frame and the housing surrounding it, which at the end can induce acoustic radiation. So in order to study this particular phenomena, you do have two possible workflow using the MSC solutions. The first one is what we call the fully coupled solution, where actually both the fluid, so the air surrounding the engine, and the structure are modeled within Actron. Another possible workflow is what we call the weakly coupled solution, where Actron will take care of the acoustic radiation only, and the structural analysis can be performed with MSC Nastron, for instance. At this stage, I would like to mention a case study from our collaboration with another company, Renault this time. And as we mentioned in the introduction, we know that the challenges in the EV development is the absence of internal combustion engine that can expose other noise sources to the driver. Therefore, during the development of a new electric powertrain, Renault wants to determine the NVH requirement of new motors before the actual physical prototyping. The solution they used was to read electromagnetic forces calculated by Maxwell 2D into Nastron. Then Nastron was performing the vibration analysis, and based on the vibration levels computed by Nastron, acoustic radiation was performed inside Actron in order to predict the noise radiation. Now, I would like to guide you through a live demo of an acoustic radiation analysis setup in Actron. So I will move to Actron VI. And before actually to set up the analysis, I will introduce you to the case we will study together. So the model we use for this demo is a 2004 Prius motor. At least we used its geometrical information to build a simplified model, and we applied a simple sine function on the teeth of the stator to create our excitation. We will use a weakly coupled solution to analyze the acoustic radiation of this electric motor. And because of that, we need to first get the structural results in order to move in Actron and perform the acoustic radiation analysis. So, in addition to the structure deformation computed when we apply a sine function to the stator, we can also look at the structural mode, because we know that they will at the end drive the structural deformation. We can look first at global indicator once we have performed the structural analysis. Here we are looking at, for instance, the mean square velocity on the stator and the housing surfaces that clearly indicate us that the structures do not vibrate equally at all frequencies, but instead there are some frequencies where the vibration are larger, as we can clearly see here on the stator, and a peak that is appearing around 2.6 kilohertz. This is also reflected at local vibration levels, where we can also make a link in between vibration level and normal modes of the structure. So, having the structural displacement information, we can move to the acoustic radiation analysis. And what is really interesting is that since Actron 18, we do have developed a dedicated wizard for acoustic radiation analysis that really allows the user to easily set up their model by a step-by-step approach. So I will now get back to Actron VI, and in order to open the wizard, I will go in the wizard menu, select the acoustic radiation wizard, and select the frequency acoustic radiation wizard, as we will perform a frequency acoustic radiation analysis. When you do that, you do have a window that welcomes you to the acoustic radiation wizard. And to start to build your analysis, you simply click on Next. We clearly see and directly see on the left-hand side of the window what will be the steps required to define our model. We'll first select the structural model we want to use. So what are the structural results we want to use for acoustic radiation analysis? We will then select the analysis parameters to move to the acoustic model definition to define the acoustic environment surrounding the structure that is radiated. Then the coupling parameters that will trigger the projection of structural result to the acoustic model. And finally, the output we want to have at the end of our computation. But I will start with the structure model. In this example, my mesh is stored under OP2 file. So I will go and select my OP2 mesh. The mesh is directly loaded inside ActionVI in the background. The results I have are vibration pattern for a defined set of frequencies. And actually those results are stored within the same OP2 file coming from Nastran, and so I'm selecting this OP2 file. For the rest of the parameters, I can keep the default value because I have stored displacement result, and I can directly move to the analysis parameters. So in this second step, we need to define the frequency we want to use for our acoustic radiation. In my case, I will use the same frequencies that were used for the structural analysis. So the frequency will be imported from a file, and this file will be once again our OP2 file. So once this is done, we can move to the acoustic model definition. We have several strategies that we can use. And the one we will use today is create our acoustic mesh surrounding the structure using the ActionVI meshing tools. So I select this strategy, and the first thing we need to do is actually fill the holes of the structure. As we can see, the structure is not closed. So what I will do is select the structure, quickly fill the holes of it, so we can preview what will be the filling function results. So if you are happy with that, you can create this mesh and you directly come back to the wizard. Now that we've closed our structure, we will create a shrink wrap, so a 2D mesh that is surrounding this structure mesh. So I'm selecting all the structure mesh, and I will create a wrap around it. Once again, I can preview the result of my parameters, of my shrink wrap parameters that are in blue now. And if you are satisfied with that, once again, you can create and go back directly to the wizard. Because we have created the first wrap that might be a little bit rough, I will smooth this mesh by remeshing it, thanks to the mesh on mesh option of ActionVI, and now we have something that is really smooth and looks great for our analysis. So I'm happy with that. I click on create. I go back to the wizard. I can keep I will define the parameters for the fluid that are surrounding the structure, so the sound speed and fluid density, and I will keep the default value. The next parameter is the thickness that will drive the volume thickness that will surround my structure. And what is really nice is that this is the only parameters you need to define, because indeed now the acoustic mesh that is surrounding the structure is created automatically by the solver during the computation, so that the mesh is adapted to the frequency you want to analyze, and so you get the best performances you can have in terms of acoustic radiation. So I will define a certain thickness, in my case like 10 centimeters of fluid around, and I can move to the coupling parameters. Here, we are defining how structural results are projected to acoustic mesh for the acoustic radiation analysis. And actually, in this case, all default parameters are fine. The structure is selected, the acoustic mesh is already selected for you, and you can directly move to the output definition. In terms of outputs, we will generate a map that will allow you to look at the acoustic radiation. And what I will do in addition to that is create a set of microphones around the motor using the ISO 3744 tool that is embedded inside Actron VI. So I can give some parameters. Once again, I have a preview of where my microphone will be located, and if you are satisfied with that, you can once again click on create. You go back to your wizard. You see in the background that the different microphone have been created, and we are done. So this is complete. The wizard tells you that the analysis setup is complete, and actually you have now an analysis that is ready to run. So you can select Open Run tab, finish. The Run tab is open in the bottom of the graphical user interface, and you can click on Run, and the run will be launched, and you just need to wait to get the results. So this computation is taking around like five minutes. So I will directly move to the post-processing of the results. So in terms of results, obviously we have defined some microphone around the engine, so we can look at the sound pressure level as function of the frequency for each of them, and also take back our structural analysis and its results and make a parallel in between some peaks we see in the sound pressure level curve and the vibration information we got. We can also look at sound pressure maps and isolate maybe some problematic frequencies and structural parts to understand where we need to work on in order to reduce the sound radiation at some frequency. So this is what I wanted to show you today in terms of live demonstration. At this stage, what I would like to say in terms of summary is that MSC really provides you with noise prediction solutions for both the electric motor and the gear reducer. But in addition to these solutions, MSC offers you also both the technologies and the professional services that can really help you to solve your industry challenges. Maybe while Ijung is gathering some of your questions, I would like to briefly talk about the FFT Acoustic Simulation Conference 2018. So like every 2 years, FFT is organizing a conference focused on topics around the acoustic numerical simulations with Actron. So if you want to learn more about any acoustic application, please register to this conference. This year the conference will be held in October in France, in Toulouse. We have a large audience and various and very interesting attendees that will present their work using Actron. And so it's really the opportunity to discuss also the best practices for acoustic simulation.